Busy?
Yeah, got to walk
Kept you
around.
busy? You also had some Zoom meeting that you.
Yeah, one Zoom meeting with John Potts from San Diego.
With John Park. Okay,
Yeah.
so that was a Zoom meeting.
Yeah, yeah.
Oh, yeah. I
Yeah, they
remember.
changed the rules for them, so
Yeah.
he's not actually physically here. He comes here a couple times a month, whereas our rep is there, he lives in West Lafayette.
So we used to have the same thing. I mean, our rep used to be here. And
Yeah.
in fact, there was a husband and wife team. They were, so one was the San Diego rep and the other one was somehow connected to team in Illinois and San Diego,
Yeah.
the husband and wife, and they lived here. But something has recently
I
changed.
just don't know why. I mean, it's so much better if they're, especially so that they can talk to people at the VP and car and all that stuff.
That is true. But I wonder if it is because for somebody who's an employee, to be away from there for a semester or a whole year, I mean, this is
They-
disruption.
But they
to the
aren't
family.
really. They aren't, well, if they bring the family with them, like Ken Patel, ours,
Mhm.
his family is with him. His daughter was in Scouts with my son. So I would run into Ken at Scout meetings. So I mean, yeah, they're fully integrated in the community. And I think that's important. And then, you know, Ken's always going back to San Diego. A lot of times I saw Ken more at San Diego than I did in West Lafayette. I went to San Diego to give a seminar. There's Ken. I'm like,
What are you doing?
Or I want to do just a brief announcement right at 4 o'clock to remind everybody about the SIP tour. It's going to be in SIP next week. And if they want to eat the food, they need to RSVP. So we order that food.
Next week or the week after?
The-
Fifth. Yeah, the fifth, 2 weeks.
Okay, okay. Apparently I'm
It's 2
forgetting
weeks.
there's an extra long October.
And,
Okay,
and,
now wait.
and you will be taking care of the ordering the pizza and so on.
Uh,
For that.
well, actually, Leon has Silvana and everything doing that, but I created a
Well,
Google
we
form.
coordinate with them.
Okay, yeah, I can
But the
totally order.
ordering, I don't know, if I can order pizza.
I can order pizza. I'll order pizza. But
Let's coordinate with Savannah and.
yeah, but I did create the, she didn't know I created the Google folder, and I was like, yeah, I've already started. So she was like, thank you. Like, we got sent her with a whole list of things to do, and she'd already, half of it was done. I was like. And so like, this should work correctly.
Now you know, you have to just click one time. And then, no,
Sit up here and do this for the 30 minutes before we get here, and then I hit the share screen, and
everything goes.
it looks like I've done nothing. Christy, you didn't get anything out of that training this summer.
So that's about it.
some online. Online, and whatever they see they have. Some of them are removed.
No, I have
We can't
midterms.
even fit everyone into a classroom anymore, so we actually
Have what?
have
That's not
people
terrible.
because the way some does it, it's like all the undergrads and the grads.
Are you getting some stress relief?
So we do have a separate seminar class on that
No.
in spring.
Don't let them pile up on the
And
end.
sort of industry
Don't
works.
let it pile up again.
And when I ran seminar, that's what I tried to do. I tried to have grads and undergrads with distinct things, every once in a while, bring them together.
Yeah, once in a while I do feel that this would be here. I did that all this would have been. Some segments of the grants.
You'll start like right at 4 o'clock.
Sometimes I think this is such a high.
It's 4 o'clock if you want to go ahead and get started.
We always have that in Michigan too, like electronics and. But I always tell my students, if you're not even going to a seminar, just to learn how a seminar is good. So you can learn how, what you want to do or what you don't.
At 4:20, and then you just have to sign on the sheet paper. So please do that before you leave if you don't get signed in. Also, this is just a reminder, you've been seeing the flyers come out for the SIP tour on November 5th. So vote early, you can come to our seminar, which is the SIP tour, and stay late for free pizza. And I want to make sure I have enough pizza for you all, so RSVP. Now I'll turn it over to Dr. Eugene.
Okay, so, thanks, Christy. It's my distinct honor and pleasure to actually introduce today's, speaker, our host, Professor Garner. Now he's at Purdue. but, he has got, several degrees actually, over the course of his career, with breaks in between, but I'm going to mention the most important ones, which he got from here as an, he got his undergraduate degree from his department some time ago. And then he went and worked for the Navy, and then got one degree, and then got another degree, and eventually got a PhD from the University of Michigan. And then came to, after another stint with the Navy, I think, GE, sorry. Came to Purdue as a faculty, and he's a faculty member there, professor, also has joint appointments in electrical and ag bio, as well as he's there, the grad core, the grad DGS, and what do you call him?
Graduate chair.
Graduate chair, is the graduate chair. So, when you have problems, what to do, you would go to him, the grad student would go and knock his door.
Yeah, not here.
What he does, he's gonna tell us, but, he's primarily plasma and fusion. And interesting things, the things that can be done. So, some of you probably are familiar with the plasma activity that was going on in CPMI with Professor, Professor Ruse's group, where, studying the impact of, plasma on chewing gum. So Professor Garner has studied orange juice and plasma interaction. Maybe he's going to tell us about what happens to orange juice when you expose it to plasma. So without taking much more of your time, Alan.
All right, well, thank you very much. So thank you for having me. Let's see if this works. Excellent. Good job. So I will be talking today about new perspectives in electron emission physics. And very briefly, I'm not going to talk about everything that my research group does, but my research group is called the Bioelectrics and Electrophysics Laboratory. And what we study is essentially electromagnetic radiation, everything from generation to actually interaction with materials. As Rizwan mentioned, one part of this is the bioelectric interaction. So we look at things like plasmas and orange juice. We also look at things like high power microwave interactions with neurons and tissues. That's something that both the Army and Navy are very interested in due to security events that happened in various parts of the country. So in addition to this, I was here 2 years ago and talked about our work on micro discharges, particularly the development of novel theories that linked electron emission with the conventional Paschen's law. Today's seminar will dive deeper into the fundamental physics of electron emission, basically trying to develop simple theories, comparison to theory, with experiment, trying to understand how much current you can put into a diode, as well as how different mechanisms that can put current into the diode will contribute to the overall current. Now, I can't begin without mentioning first the groups that have funded this research. Much of our work has been funded by the Air Force Office of Scientific Research, the Office of Naval Research, and more recently by Sandia National Laboratory, as they work on developing new generation technology and want to better understand the physics of diodes that they use for generating bremsstrahlung. So a lot of times where I come from, there's always the question, how are you tied into nuclear engineering? Well, you need to generate a lot of high power to generate radiation. So what do you need to be able to do that? You need the high voltage pulse power supplies. Our group looks into novel architecture for building those things. We also need to understand the physics of the diodes. And that's another aspect that we play a role in. And we're working with Sandia to try to collaborate on procuring a system for Purdue that will allow us to do the full benchmarking, going from pulse power system to diode and generation of bremsstrahlung, and then be able to do theory and experiment. So this slide kind of summarizes the roadmap and what is out there in electron emission physics. So you can look at electron emission physics from numerous perspectives. The outer ring of this diagram shows you the aspects of the, let's see if I can get this, that's not what I want. Let's try this one. There we go. So the outer ring shows you the different application spaces. And coming from the DoD perspective, what does DoD care about? DoD cares about applications like electric thrusters, high power microwaves, not on here, but related to that, directed energy technologies. So using microwaves and lasers for electronic warfare, Then you get into more commercial level applications, such as thermionic energy conversion. You're trying to use heat to release electrons to generate a current. At some point, you'll heat up the electrons enough to create a lot of current. When do you hit that threshold, which is called the space charge limited current? Okay. Then you've got other applications such as photo emission in nanogaps, nano vacuum transistors. So multiple applications that span national security and commercial applications. In addition, you have different phases of matter. For instance, traditionally, a lot of electron emission physics happens in vacuum, such as vacuum tubes, where a lot of the initial work was done. But doesn't need to. I mentioned the work that we do in microdischarges, right? Microdischarges occur at atmospheric pressure. So you're interested in the electron emission mechanisms at quote unquote a high pressure. So understanding the mechanisms of emission physics going from vacuum to atmospheric pressure is important, not just theoretically, but from a device perspective. You can also look at emission physics in solids. There is a space charge limit derived in the 1940s for semiconductor material that represents the maximum current possible. That's been around for 80 to 90 years now. You can also demonstrate the same physics in liquids, and that can become important. You can imagine looking into high voltage in liquids for, say, combustion, right? And as you apply higher voltages, you can have a phase change from liquid to gas. So how does that affect the emission mechanism? That is something else that we have studied theoretically. And then you can put this all together and go all the way down to nanodiodes. So you can get down to these pressures where the mean free path becomes very small, and you can go to distances even smaller than that. And you can start to get into quantum effects, which we've also studied theoretically. We've developed theories that link all the way from quantum level all the way to Paschen's law for avalanche. So our group's interest in this field, I mentioned the microscale gas breakdown work. This is a book chapter that we published that summarizes that work. I gave that seminar here a couple of years ago. Today's talk will focus on what we call nexus theory. This is the unification of these different emission mechanisms. And the reason you want to do this is that you can derive theories that solve exactly for the current density and voltage in your diode. You can also use simulation software, particularly particle and cell simulation. Particle and cell simulation looks at representing the particles as a group of macroparticles. So a single macroparticle represents multiple real particles. And you can put these in complicated geometry. The problem is it can become computationally expensive. So can we leverage our simple theories to guide these simulations? By looking at multiple mechanisms and using what we call nexus theory, where these mechanisms intersect, we can determine when we can focus on a single mechanism or two mechanisms so that we can make our codes and our theories as simple as possible. And then the final one I'll talk about today is non-planar space charge limited current. Space charge limited current in a vacuum device was first derived over 100 years ago by Child and Langmuir. Very simple derivation. It's 1D inspired is a good way to put it, because you're looking at an electrode that is infinitely long with emission from an infinitesimally small patch in the middle. The solution in planar is very straightforward. I'll summarize the steps. As soon as you go to spherical and cylindrical geometries, even in one dimension, things become a lot more complicated. And my students, Adam Dar and Harsha, spent a lot of time looking at this and developed several techniques to actually derive that solution, which seems simple, but it took almost a century to actually come up with the solution. And Harsha is working on a manuscript now that finally connects that solution to a multidimensional geometry. So we'll start with a conceptual understanding of electron emission. So the whole point of electron emission is you have your diode, so you have a cathode and anode, and you do something to the cathode such that the energy of the electrons exceeds the energy barrier, or what we call the work function. So you have to give the electrons in the cathode enough energy to exceed that. And here in the diagram, you see some simple examples. You can shine a laser on the cathode, excite the electrons to be released by photo emission. You can heat the cathode often up to several thousand Kelvin, okay? That's thermal emission. You can apply a very strong electric field. This is what happens in microdischarges. At microdischarges, as the gap becomes small, the electric field at breakdown becomes strong, and you can strip off electrons. that leads to a deviation from the traditional avalanche condition. The avalanche condition is what you see here. You see the electrons coming and they ionize particles, create more electrons, continue to ionize. And then you have secondary emission, which plays a role with that, and that leads to Paschen's law. Okay? So the focus of today's talk is to try to understand the relationships between these three mechanisms, okay, and the space charge limited current, which is the maximum current that you can inject into the diode. Now, in a field emission case, where electrons are emitted with no initial velocity, often called cold emission, okay, you get a field distribution that looks like this. So this gap is looking at the electric potential versus location in the gap. Now, talk about this also in radiation detection when you're talking about gas detectors. If you have no space charge in the gap, the electric field in the gap is a constant, and the electric potential varies linearly. So it goes from ground at 0 volts to the diode voltage, okay? And that's J equals 0. As you put in charge into the gap, it becomes harder and harder to put in more charge. Basically, you're building up a space charge layer, and it's harder and harder to put more charge in. So what you see is that the electron potential starts to become depressed. At some point, that electric field at the cathode becomes 0. That is the traditional condition used to derive the Child-Langmuir law in vacuum with no initial velocity. Now, if your electrons have an initial velocity, such as you have thermal emission or photo emission, this is no longer the condition. What happens is you get what's called a virtual cathode. So that 0 electric field point shifts into the gap. And as we'll see, there are different conditions that were derived first by Langmuir and then by other folks that mean different things physically. But conceptual thing to understand, with no initial velocity, its electric field equals to 0. You can also derive the same condition in multiple ways. One is by vacuum capacitance. You can make an argument about how much charge can be held in the gap. I'll use this later, okay? The other condition is that the Child-Langmuir current density is the maximum current density allowed. And that becomes important later as well. This is a conceptual diagram of the same thing, just from a different perspective. So for small gaps and low pressures or low collisionality, you start off at Child-Langmuir. That's the space charge limited current in vacuum. Collisions, that's Mach-Fermi. Then you can have your sources. So field emission, thermionic emission, or thermal emission, those become more important. And then as you get to larger gaps, you can get to the traditional avalanche condition. So this is a kind of a conceptual diagram of these mechanisms and the ranges where they operate, as well as some seminal review papers that cover these different mechanisms. So now I'm going to get into some math. And the reason I show this is not to inundate you with math, but to show you that the fundamental derivation is straightforward. So, and a lot of these things have analogs. I'm teaching our Intro to Nuclear Engineering course this semester, and the biggest challenge I have is switching between languages. So when you're taking a Lamarche class, you deal with continuity in chapter 5 and 6 of Lamarche. You're looking at neutron continuity. It's the same physics, okay? So we have continuity of the electrons, electron charge times number density times velocity, okay? We deal with Poisson's equation. You wind up dealing with Poisson's equation also with fixed law as soon as you start looking at the different aspects. The only difference is that Lamarche calls this a flux and not an electric potential. So I have to be very careful, and I always screw this up when I'm lecturing. I wind up eventually saying potential because I'm just used to calling it potential. But it's the same physics. You've got this Laplacian of the potential, and it's equal to the current density divided by the permittivity of free space divided by the velocity. This Laplacian makes things very complicated. You wind up with singularities when you're dealing with Child-Langmuir, okay? And then, of course, we have the force law, standard kinematics, we called it Physics 107 when I was a student here, but basically the second semester physics course, all right? So you can use these and solve directly for the Child-Langmuir law. What you can also do is put in a canonical current source. In this case, we assume the canonical current source is field emission, given by the Fowler-Nordheim current. You can then combine these equations, do a trick called non-dimensionalization to eliminate all the material properties, and then you can take asymptotic limits. In the asymptotic limit of high voltage, you recover the Child-Langmuir law, which goes as v to the 3/2 over d squared, okay? In another limit, you can recover what's known as the Fowler-Nordheim current density. So that is the field emission. And then you can match these asymptotes and come up with what we call a second order nexus. So the second order nexus is the Child-Langmuir law equal to Fowler-Nordheim. So if you're above this curve, your space charge limited. If you're below this, you're field emission driven. And if you're in between, you have to use the exact solution you derived here. Okay? And then this equation can be solved analytically by setting these equal, and you come up with an analytic solution for that curve. And what my student Wong did was he actually looked at this experimentally. So he did an experiment with these nano devices that we purchased from the University of Chicago during COVID. So it took several years to actually get them from them. But you see here, we're looking at different aspect ratios. As you raise the voltage, you can see during the breakdown, you eventually just completely obliterate that other electrode. What was interesting is we plotted the breakdown voltage. You see that the breakdown voltage varies roughly linearly. We derived this theoretically. I talked about this in the seminar 2 years ago. But this can be shown from first principles linking field emission to avalanche breakdown. This part is not. And what we determined this to be was when we went to high enough voltage, we started to obliterate the electrodes. And at that point, it didn't matter how high we raised the voltage or how big we made the gap, you were obliterating everything. So you see the voltage actually plateau here. But we can see that we're field emission driven. This is what's called a Fowler-Nordheim plot. If it's linear, you're in the Fowler-Nordheim regime, and then you get the spike. The spike is the actual breakdown event. We then plotted that second order nexus that I talked about earlier, and we put in the beta, which is the field enhancement factor that we anticipated based on our experimental design here. And we see that we're very close to the transition between Child-Langmuir and Fowler-Nordheim, which is what we would expect with those parameters. But we can also look at the same thing with collision. So this was work done by one of my PhD students, Adam Dar, who's now at Sandia. We took the same basic physics I talked about earlier. So electron continuity, Poisson's equation, Fowler-Nordheim, but now we modify the force law. This term here is electron charge times velocity divided by electron mobility. So this is actually acting as a friction term. And that friction term introduces another asymptote known as the Mach-Garner law. The Mach-Garner law is the space charge limited current in collisions. So we now have what we call a third order nexus point shown here. So this third order nexus corresponds to Child-Langmuir, Mach-Garner, and Fowler-Nordheim matching, which is interesting. So when you're at a small enough gap distance, it looks like vacuum because you're below the mean free path. When you exceed that gap distance, you see you pass through Mach-Garner first. Similarly, if you go to a high enough voltage, it always transitions to Child-Langmuir first because you're giving the electrons enough energy that they go through the gap. Okay. You can also look at the same thing with respect to electron mobility. If the electrons are really mobile, it looks like vacuum. If they're less mobile because there are more collisions, you go to Mach-Garner. Now, this third order nexus is interesting from a practical perspective because if you're at atmospheric pressure for nitrogen, which is kind of like air, okay, that third order nexus happens right around 250 nanometers. So you're starting to get close to that microscale breakdown that I talked about earlier. And my student Wong also did experiments at atmospheric pressure. And what he showed is that if you put in the parameters for the devices, the operating space, which is this magenta X, is very close to that third order nexus. So the emission can look space charge limited when you're at breakdown sub 1 micron. And in fact, he saw that experimentally. You can kind of see that here in his Fowler-Nordheim plot. You see how it's linear, and then it kind of plateaus. This is indicating the contribution of space charge. And then you have the breakdown that happens after that. So this was the first clear time we saw in print. We'd seen people say it, but we hadn't really seen it in a publication where people actually showed the breakdown from a space charge, maybe not limited, but certainly a space charge dominant regime. So you can even do more cool things with this. This was recent work funded by Sandia, done by Lauren Breen. What she looked at was combining collisions, field emission, and thermionic emission, okay? And by doing that, she introduces a different canonical current density called the general thermal field emission current density. And that was developed by Kevin Jensen from Naval Research Lab. And then you introduce a new asymptote, which is basically the Richardson-Loud-Dushman equation for thermal emission.
And what was interesting in what she did, she saw all these transitions that we saw earlier, right, between the different mechanisms, but she was able to derive a modified Moncrief law that accounted for initial velocity by taking the asymptotic solution in the appropriate limit. What she also showed was something that Adam and I noted, but we didn't operate in that regime, was this rapid drop here at this mobility. We thought at first that was a numerical thing, but it's actually physical. What this is telling us is if the gap becomes too collisional, it doesn't matter what voltage you're at, it's space charge limited. Because it's so collisional, you can't put more current in. So that's actually a physical thing. And then if you apply enough voltage, it eventually hits the Child-Langmuir limit again. Okay? So that is nexus theory. That shows the utility of understanding mechanistically what source currents dominate. But everything we did there was assuming one-dimensional planar geometry. The real world is not one-dimensional planar. And people have been trying to solve this for a century with different degrees of success. The common case used for non-planar is what's called the Langmuir-Blodgett equation. Okay, Langmuir and Blodgett derived this for concentric spheres, concentric cylinders. The issue with their derivation was that they used power series approximations. And I was fortunate enough when I was a student, I took Calculus 2 here at Illinois. I took it through the Calculus and Mathematica program. And they spent a lot of time emphasizing not really the paper pencil part, but the conceptualization of why we were doing the paper pencil part, which as engineers and applied physicists is actually the more important part, because you can actually look up or use Mathematica or MATLAB to do the mechanical part. But one of the things you think about when you're taking a series expansion, right, and you're looking at the point to expand upon, one thing that I would always look at is not taking an expansion about a singularity. They actually took their series expansion around a singularity, which is somewhat dubious. So, but other people have tried to improve this, but with limited degrees of success. So one of my suite mates before we changed buildings was using variational calculus for the two fluid flow problem for reactor protection. And I'm like, what does variational calculus do? It looks at extremization of functions. What is space charge limited current? It's the extremization of the current density in the diode. So Adam, when he started as a PhD student, he'd taken this class as an elective. He was a physics minor. And we started to look at using variational calculus. And what variational calculus does is it gives you what is called a coordinate invariant solution. In other words, the base solution does not depend upon the coordinate system that you're in. So this equation is not necessarily exciting. This just couples all those equations I had on the first slide. So there's nothing new here. But then you apply what's called the Euler-Lagrange approach, and you can derive this solution from this. This is important. So this is showing the Laplacian of the potential is equal to the gradient of the potential squared divided by 4 times the potential. This is exact from first principles and is coordinate system invariant. Now, obviously, depending on your coordinate system, you may or may not be able to easily determine the Laplacian or the gradient. But it is applicable to numerous geometries of interest, even something as simple as a sharp-tipped electrode, which still has many applications in microplasmas and electron emission because you can really concentrate the field. So Adam took those equations, recovered Child-Langmuir because everything has to recover Child-Langmuir for 2 plates. But then he derived these solutions for cylindrical and spherical geometries. We also compared to some of our labels seem to have gotten deleted, but we also compared to the traditional Langmuir-Blodgett solution. We compared to other things in the literature, but what's important to realize here is these are the first solutions completely from first principles in a closed form. My other student, Harsha, in parallel, was taking a complex variables course and was talking about conformal mapping. So he's asked the question, can we use conformal mapping to do the same thing? Because at the end of the day, you've got this maximum current density. What is it a function of? It's a function of the electric potential. And electrical engineers, they don't talk about it much, but there are textbooks where they actually use conformal mapping to map the electric potential. So if you know the space charge limited electric potential, you can use conformal mapping to map it to different geometries. And lo and behold, you get the exact same solution that Adam got using a physics-based approach. So important to realize, Adam Darr's approach was looking at the physics. He was looking at extremizing the current. using variational calculus. Harsha would take the planar solution, the electric potential, and be able to map it geometrically just through the geometric argument. But they give the same answer. So alone, no one would have done this, okay? Because it's kind of hand wavy in a sense, right? Even though it makes sense physically. But once you have the physics solution, then you start to look at other things. And the nice thing about this is there are mappings from many complicated geometries. I took those out, but there are many complicated geometries in the paper for which you can map the potential. So there's a lot more utility. But, you know, we got a comment from a reviewer, and the reviewer said that we were violating the electron continuity condition. So one way to think about this, when I thought about it, I said, well, we're using electron continuity to derive the equations. How can we violate the condition that we used to derive it? So we thought very hard about this, okay? And we published numerous papers on this after we thought very hard about this. One of the things that electrical engineers struggle with is that everything electrical engineers do is by definition multiple dimensions, okay? Anyone that's taken the fusion class, right? And you start talking about E cross B drifts and magnetic field effects, right? All those effects are inherently 3 dimensions. You look at Maxwell's equations, you're starting to do things like curls and divergences, right? All those processes are inherently 3D. Now, let's take the simple example, Cartesian. You look at your differential length vectors, dx, dy, and dz. What you'll notice, first of all, is these all have units of length, right? And they're all independent of one another. So if you reduce Cartesian coordinates from 3D to 1D directly, everything works out, okay? That is actually dumb luck because of the way a Cartesian coordinate system is set up. Now you go to cylindrical, okay? Cylindrical, you've got a dr and a dz, they're independent, they're linear, happy. But if you start looking at phi, what are the dimensions of phi? There are none, they're radians, right? There's no unit. So when you start talking about differential length in a phi component, you have to put in the r. So as soon as you put in the r, or if you're going into spherical coordinates, right? You've got a theta and a phi, which one is which depends on whether you're a physicist or an engineer or a mathematician, but regardless, you've got 2 angles. You have to have the r there for the differential length. So the coordinates are not independent as soon as you leave Cartesian coordinates. There's this interdependence, okay? So when you start to talk one dimension in quotes, right? For spherical and cylindrical, you do not just blindly apply a divergence, like what the people making the comment, because physically, if you think about what's happening as you're going into R, right? You've got these theta and phi and z things that contribute, okay? Those angular things. So if you're just going into R and you're not thinking about those other dimensions, you're not physically doing the translation. You can't use the 3-dimensional things with 1D unless you correct for doing that. So I was talking about this with Harsha on a WebEx call because this was during COVID. And I started to ask the question, okay, who else would care about it? So coming from nuclear engineering, who's the first person you think of? It's the fluid mechanics people, right? We've all taken that fluid mechanics class as an undergraduate, right? Where you start talking about flow through pipes. It's the same physics. You've got to flow through a pipe and you're only considering one dimension. So I Googled a fluid mechanics book and I found the correction factors that we were able to use to correct from 1D to 3D. So what are the main issues here? One is a curl. A curl is a 3-dimensional operator. If you're going to do 1 dimension, you have to make sure you account for that translation or else you get garbage out, okay? Current densities, that's another issue. A current density is by definition a 3-dimensional quantity because it's in amps per meter squared. So it's a normal quantity, right? If you think back to doing your neutronics. So it's going through a cross-sectional area. So it's flowing in one direction, cross-sectional area in the other two. It's 3 dimensions. So if you're doing something in 1 dimension, the correct unit is amperes. If you're doing something in 2 dimension, the correct unit is amperes per meter. So you have to make sure you're accounting for the right physics. Okay, so this requires corrections by multiplying by the appropriate corresponding orthogonal coordinates to make sure that you're accounting for that 3D effect so you can actually use the standard Maxwell's equation. Harsha right now is starting from Maxwell's equations and actually validating this, going from multiple dimensions to 1 dimension. He should be ready to submit that manuscript soon. That was part of his dissertation. And he also published this in great detail in a recent PhysRev paper. So that leads to the next thing. So everything we talked about so far is cold emission, but we can also have thermal or photo emissions. They have non-zero velocity. So child Langmuir needs to be modified. So when Langmuir first did this, what he tried to do was to shift the location of the virtual cathode, right? I mentioned that the electric field was no longer zero at the cathode, it was zero inside the gap. So there are two ways you can think of doing this. One that was developed is basically what's called the bifurcation solution. You can kind of see that here on this graph. So this is the electric field at the in the gap. This is essentially a representation of current. It's a little bit more complicated, but essentially it's the current. So you can see here, this is the maximum part, right? This is the space charge limit. This is the bifurcation solution. The bifurcation solution is physically what was thought of as a virtual cathode corresponding to the Child-Langmuir solution. Remember, Child-Langmuir was zero velocity. So this bifurcation solution is zero velocity at the virtual cathode. That gives you a reflection. That's actually very important because it can generate noise or it can generate a microwave signal. Okay, so you have two solutions. One is bifurcation. The other is the true space charge limit, which was derived by Jaffe in the 1940s. Okay, so one of my undergraduate students, really sharp guy, had already up the differential equations his first semester at Purdue. We're like, hey, can we take our variational calculus and apply it to that problem? We thought it would be easy, but wound up being more complicated. So the Euler-Lagrange equation is deceptively simple. You just basically include this initial velocity term. The actual math starts to get complicated because you have to be able to account for the locations of the virtual cathodes. But he was able to eventually solve for it and show that the bifurcation current density is the Child-Langmuir current density times this correction factor. And that holds for not just Child-Langmuir, but for any geometry. So as long as you can calculate this current density for any geometry, you just have to multiply that correction factor. Then to derive the space charge limited current, it was a little bit more complicated using variational calculus. The big takeaway here is that you can get to a solution, but it does not have a closed form solution. You have to integrate this and solve it numerically. But you can come up with a solution. So here you see the exact solution in green. You can see a numerical solution with the red points, good agreement. And then you have the bifurcation solution underneath. We can also look at the shifting of the virtual cathodes. The takeaway here is that the virtual cathodes tend to be next to each other, either the bifurcation or the space charge limited current. But what Harsha wanted to do was make this a more general approach. So he came up with this fancy idea called Lie point symmetry. The first order, this is very much what we do in a Lamarche class. What you do is you start off with your differential equation, and then you use a quote unquote symmetry. All the symmetry is the substitution to take this and reduce it to an ODE, which gives you a solution like that. It's just like what we do with the different geometries in a Lamarche class. Same technique, but by calling it Lie point symmetries, it opens up the ability to use multiple geometries that are more complicated because these symmetries exist for many geometries. So he reduced it to this, took the maximum current, and recovered the same solution that we obtained using variational calculus and conformal mapping. But he was also able to incorporate the non-zero velocity. So he obtained this Jaffe correction factor that I showed on a couple of pages ago, but for any geometry. So what's very interesting about this, you go back to Langmuir and Blodgett in the 1920s, they had all these techniques at their disposal. Variational calculus, conformal mapping, Lie point symmetries, these have all existed for probably several centuries, but they did not actually look at using these approaches, but they all yield the same result. So, oh yeah, go ahead.
What is beta in that?
Beta is, I always get this confused, but it's the ratio of the potential energy to kinetic energy. So E times the voltage divided by mv squared over 2. I have to look to make sure which is which, but it's that ratio. It's not the other beta that you might be thinking of. Okay, so collisions. Everything I've talked about so far has really been vacuum. But even in vacuum, you can have damage of materials, you can have imperfect vacuum. So what Lauren looked at was deriving a space charge limited current that was general for initial velocity and collisions. So to do this, she started from the basic force law that I showed many slides ago, but she took out the canonical current density and just solved for the maximum current allowed by taking a derivative. What she could then do was plot the space charge limited current as a function of transit time and the voltage as a function of transit time, and plot those parametrically as a function of the transit time. That gave her space charge limited current versus voltage, okay? And then she came up with all these other things that you need to plug in. And then she took the limit of high collisionality. This is now collision rate and not mobility, because plasmas makes it more natural. And she recovered again a nice solution for the non-zero initial velocity Mach grenade. So this was very nice. The reason we needed this was we were solving the cross field problem with a perpendicular magnetic field, and we were about to scale it and realized we didn't have anything to scale it to. So we had to derive this so we had something to scale. But again, things are not always planar. So this is work done by one of my undergraduate students from physics. And what we did here was we took that concept of what we call canonical gap distance that came from lead point symmetry. Basically, all these symmetries say is that you can start from your planar solution, Child-Langmuir, and put in the appropriate canonical gap distance that translates from one geometry to another. So I speculated, Harsha derived formally mathematically, that we could actually apply this. So this plot here is for a given velocity, temperature, mobility, and this gap distance, but this is a script key. This is the canonical gap distance. You can then use the appropriate mapping to translate it to your geometry. And that's what we did here. Adam Dar, who's now at Sandia, used a particle and cell simulation called Empire from Sandia, put in a tip to plate geometry. We then compared that to the theories that we derived before, but with the canonical gap distance, and then translated to the physical gap distance for that geometry. And you'll see here we get very good fit. You're following the thermal emission. At the end, you're following space charge limited emission. And then in the middle, what you're seeing is the addition of the thermal emission with the field emission, hence the simulation predicting above that. So exactly what you would expect theoretically. But can we do better, or at least differently? So remember before I told you that you can derive the maximum current using capacitance. So what I did was I made a capacitance argument. So from Lorentz theory, we know that electric field is equal to the current density times the time when the initial velocity is zero. We can make a capacitance simplification, and it comes out to be identical. When you rearrange and you non-dimensionalize, these two equations are saying the exact same thing, okay? So that was good. Now what we say is that the electric potential in the gap is the voltage times x over d to the c power. That exponent represents the space charge. Now, in vacuum, that value is 4/3. In Mach-Gurney, it's 3/2. When you're in between, it should be in between. So using this capacitance argument, I was able to derive that exponent that goes in here. And it's only a function of the product of the collision frequency and the transit time, which essentially gives you the number of collisions in the gap. So as the number of collisions in the gap goes up, you start to hit that Mach-Gurney limit. When it goes towards zero, you go back to 4/3, which is vacuum. But we can do more with that. We can go back to the force law and then the Poisson's equation, okay? We go to Poisson's equation, we assume that, first of all, we know how this behaves, right? We know the second derivative goes with this, and then we can use that to solve for the velocity. We know how the velocity must vary with position. Then we can put that into the force law, come up with this dependence, and we look at the anode at x equals d, and we can solve for the maximum velocity in the gap. The nice thing is that this maximum velocity is now analytic, okay? It's making some assumptions about the dependence, which aren't quite true, but as we'll show, it doesn't really matter when we calculate the space charge limited current. So we can calculate the transit time and then calculate the space charge limited current. So this is an exact equation, making the assumptions on the spatial distribution that we can then take appropriate limits in the limit of collision frequency much less than 1, collision frequency much greater than 1. We can take the Taylor series expansions, right? And then as you go to zero infinity, right, at zero, you recover Child-Langmuir, at infinity, you recover Marconi. Then we do a matched asymptotic analysis. Space charge limited current is a function of voltage. You can see in collisional, the exact solution matches really well. And then as we go to higher voltage, when you should be at Child-Langmuir, matches really well. And then you see the traditional difference when you're right around unity. And then what we can do as we break that out a little bit more is we can actually look at how those exponents, this is the exponent, the chi is telling you how well we agree with Lauren's exact solution. Generally speaking, we're within 7% of the exact solution, but we now have an analytic solution that you can put into Excel, which is how I plotted this. I used Excel. So you have something experimentalists can readily put in, or someone doing a simulation. So what's interesting is you can go to the simulation, right, using PIC, and you can plot the electric potential versus position and actually see how it varies and use that to determine your collision health. And then finally, we can go to multiple dimensions. Harsha went through and did a formal derivation using variational calculus, and he showed that the space charge limited potential is a function of the vacuum potential with no charge. That vacuum potential can be determined from the vacuum capacitance, which can be determined analytically from many geometries, because people did that 60 or 70 years ago. Or if you're using a complicated geometry like we are doing, you can use COMSOL and solve for it. Then you can put that into the equation for the space charge limited current that looks like that, and you have a solution. Or you can use this one, which is more readily apparent, or this one where you're explicitly using the vacuum capacity, depending on what you have. So what this does is it accounts for these fringing fields that arise when you hit the edges of the electrodes, okay? And we get really good agreement. So solving exactly, you come up with this ratio of 2D to 1D. These are hypergeometrics, elliptic integrals. The reason you come up with those is those fringing fields, or what we call hot wings, okay? And you can actually do some algebraic simplifications using series expansions, and you can show that you get really good agreement in the appropriate asymptote. And then we did particle and cell simulations using VSIM. Our partners at Boise State did this, and we're generally within about 15%, which with PIC is pretty good. The biggest difference happens when the width and the gap distance are about the same. So what does this allow us to do? I've shown you a lot of theory, right? Why do we care? Practical thing, right? When you're making a simulation tool, you want to be able to benchmark it to something. People have been using Langmuir-Blodgett for decades, since they've started to develop these PIC simulations. They have never come up with good agreement with Langmuir-Blodgett. So, of course, the computational people blame the theorists bring the computations. And even a lot of the computation people figured that was due to the grids or the number of particles or whatnot. But using the approach that Harsha is working on publishing now, where he determines the space charge limited current for a multiple dimension cylinder, he is actually right on within maybe 5% of the particle and cell simulation for a cylinder, okay? Because we've gotten complaints from some simulation people. They say, we're simulating this, we get exactly Langmuir-Blodgett. But what do you put in for your current source? We put in Langmuir-Blodgett. Well, of course you're going to get Langmuir-Blodgett out if you put in Langmuir-Blodgett. These people are not doing that. They're just emitting current and figuring out the maximum current that you can actually have in the diode, and it agrees with Harsha's theory. So we're hoping to publish that soon. I'm trying to get Harsha to finish the paper now. So what does this give us, though? Well, we have this suite of techniques that allow us to derive analytic, or at the very least, very simple things you can put into MATLAB, right? Very rapidly. So you can do design screening using theory and then extend that to simulation so you can minimize the simulation time, right? The other thing I was talking with some of the faculty, I think Rizwan even, you start talking about multi-physics, right? So you start talking about thermal effects and structural mechanics, things I did when I was in industry, right? You're trying to combine multiple effects. If you can use theory to guide those assessments, right? Use theory more and more with more realistic geometries, then when you go to the simulation, you're only simulating a more narrow range. So you're actually saving time at the end of the day, okay? So what are we working on now? Right now, we're looking at emitters. So a lot of times you have arrays of very sharp tip emitters, but trying to actually look at the transition of mechanisms is very complicated, right? Because you've got arrays. What if we can replace that with an effective capacitance? Then we can use the techniques we've developed here, develop an effective canonical gap distance and look at the translation between mechanisms. And we can do that very rapidly using theory to help guide the simulation. Also, relativistic diodes, the devices that I mentioned earlier that we're trying to bring to Purdue. Eventually, you can operate those at a megavolt. You start to get very close to relativistic effects. We have a paper right now under review with physics of plasmas where we actually apply some of these techniques to relativistic diodes. Then we can start to expand this, looking into nexus approaches, things of that nature, and really start to better understand these systems. And then the final part of all this whole thing, I mentioned before, my group also does novel pulse power design, right? Looking into these systems. What my vision here is to work at Purdue, bring in University of Illinois as a collaborator, work with Sandia, and do everything from the fundamental pulse power system development. So things like Marx banks, things like pulse forming lines, right? The left part of my block diagram. Then go through the waveguide and such that we'll get from Sandia to the diode, where we can look at the diode physics that my group looks at. And then ultimately generate Bremsstrahlung and try to look at the effects of electronics. I'm part of the scale program at Purdue where we look at radiation hardening of electronics. You can start looking into radiation detection, material effects. There's a lot of potential physics and things that we can do that couples everything from fundamental first principles theory to particle and cell simulation, DFT, Monte Carlo, experimental materials, radiation detection, electronics. So that's my longer term vision. This is just one little piece of that puzzle. And finally, particularly the faculty know this, I couldn't have done much of any of this without my students. Adam and Harsha were instrumental in getting the variational calculus, conformal mapping, coming up with those ideas and executing. Jake Halpern, I talked briefly about one of his papers. He's also the lead author on the relativistic paper. He's a PhD student at Columbia. Wong was instrumental in doing those experiments during COVID and getting that done. Lauren Breen, I mentioned, she's going to wrap up her PhD here in the next year and a half. Sarah Lang, I didn't talk about her work. She put in photo emission. She also looked into liquids. And then Alex Sinelli is an undergraduate student in physics. He's the one that looked into putting the canonical gap distance developed by Harsha, putting that into nexus theory. And then Allison Komerska has been doing molecular dynamics simulations so we can understand emission mechanisms and have another benchmark in addition to PIT. And that's my backup slide. So with that, I'm open to any questions. Thank you.
Any questions from I think? Yeah, back there. Loud.
Louder, okay, so
That's good.
thank you very much for the talk, that was very nice. Two little questions maybe. One, for the inclusion of that non-zero velocity, did you make any assumptions about the directionality of that velocity? Or was it more just a speed going in a particular nice direction?
Yeah, so as you notice, we were doing 1D in the derivation, so it's only going to go in one direction, which is across the gap.
And the second one was, I think, on slide 28. You
Okay.
had, I think you're going through some asymptotic expansion.
Yes.
It looks like you have more than just like the usual zero order, first order, and you go to the second order. What benefit do you get from the second order and beyond that made you want to include it?
I was just doing it for completeness. I mean, really, like I said, when I plotted these, I just strictly used the maternity and child labor. So I just included this for completeness.
Okay.
Hey, any other questions? I've got a couple.
Oh, wait, there's one there.
I have one quick question. Maybe it's not really the theory, but the theory is a little complex. So I'm wondering that we know the theory can be maybe the universal theory. So if we want to solve some real case like for the material, if we want to look at the material, the surface may be not uniform. So in that case, can we also use the theory
Yes.
to develop?
Yes, so Harsha published that. It was in an IVEC paper that's now out in press. He used self-defined roughness. But in principle, you know, I talked on the last slide, I was talking about emitters. Emitters can be thought of as surface roughness. So as long as you can determine the capacitance, which is straightforward to do with a self-defined layer variation, then yes, you can. Yeah.
So, question,
Uh-huh.
spherical geometry, any use for it and,
No.
when, no?
No, but it is a toy case for benchmarking the simulation. They'll use that and then the cylindrical one.
Cylindrical is more appropriate.
Yeah, yeah, yeah.
Geometry. Did you, get any of the symmetry, et cetera, from Professor Axford? And did he talk about in any of his classes?
No, I never actually took one of his classes, so no.
You never took any of his classes?
No. Yeah.
So Professor Axford was a faculty member in the department a long time ago, and he was kind of the world expert in the groups and improved algebra and symmetries.
Hmm.
So,
But it makes sense because like I said, the first step in the Lamarche book is actually at least symmetry. It's just that Lamarche never talks about it, but that is the first step, right?
yeah. What does this have to do with orange juice?
This
Where
part,
does orange juice come in?
no, this part did not. That's the other part of the group. I can come back and give another seminar on that. Actually, I did. I gave that seminar 12 years ago.
Okay.
A whole new semester.
Yeah. It's a whole new decade.
Okay, last call. One more question back there.
Yeah.
A couple questions. One of them basically talked about, how you derive the equation from Euler-Lagrange.
Uh-huh.
Have you looked at maybe like in figuring out the quantum mechanical correction after Euler-Lagrange, like maybe through like a static formation?
Okay, so what we're looking at now is not quantum, right? So it's however, that's an interesting point because there is a quantum version of child linear. We just have not operated in that regime, so that's interesting. And that could go to something like I was talking about, maybe getting in like 2D materials, where a lot of these emission mechanisms change. And that could become very interested there, especially as you get down to the quantum regime. So that's a good point.
Yeah, and my second question was, when you basically, like you're building like your Lagrangian to, derive these Euler-Lagrange equations. Can you like introduce like the symmetry right from there? Into the Lagrangian?
Maybe, but we didn't pursue that. We just did it by brute force applying the Euler-Lagrange equation.
Because I know that that's a technique in like, that they use in like,
No, we didn't do it that way. We approached the lead point symmetry straight from the equation, which made it very straightforward when we actually derived it, not from the Euler-Lagrange.
Thank you.
Yep.
One more call. Last call. Okay, let's thank Mr. Garner one more time. Thank you very much. Well,
Harsha, I think he's at like third. I'm trying to get him to finish. He's at like 5 different like per paper. I'm trying to get him to finish them, but almost finishing it. Because he's staying for a postdoc until late calculates. So I'm trying to get him to finish it. Because once students leave, as you know, it's hard to finish.
Same thing. I was checking out names and I was like, that one's some BS. We need to be doing a field trip.
Yeah, so,
Hey, there's a chat. I don't know if we want to answer it. Is spherical space change limits might be relevant? Yeah, okay, great.
Hi.